Chemical Equilibrium, Part 6, the reaction quotient Q and applications of the equilibrium constant KEQ. Let's do a review using an equilibrium a lot of people are familiar with. This is the Earth's water cycle. In this equilibrium, surface water evaporates and goes into the atmosphere, and atmospheric water condenses and goes back down to the surface. At equilibrium, these two processes are in balance. The rate of evaporation equals the rate of condensation. When that happens, the amount of surface water remains constant and the amount of atmospheric water remains constant. That's not to say that these two processes stop. In fact, not at all. They continue. It's a dynamic equilibrium. The amount of surface water does not equal the amount of atmospheric water at equilibrium. There's always more water at the surface. But the surface water amount remains constant and the atmospheric water amount remains constant at equilibrium. Now that's a temperature-dependent relationship. That's true for every equilibrium. Let's say that we took the Earth and we cooled it down a lot so that ice began to form and we went into another ice age. A new equilibrium would be established at that lower temperature. There would be a lot more water at the surface and a lot less water in the atmosphere in that new equilibrium state or equilibrium mixture. Once again, the rate of evaporation would equal the rate of condensation, but both of those rates would be smaller at that lower temperature than they were before. You can imagine that it's harder for water to go from solid form to gaseous form than it is to go from liquid to gas. So less water would evaporate, and because there's less water in the atmosphere, less water would condense. So because an equilibrium is temperature dependent, it's pretty common that we specify the temperature whenever we're dealing with equilibrium. Let's talk about chemical equilibrium here. Let's say we have this equilibrium reaction where A moles of A and B moles of B is in equilibrium with D moles of D and E moles of E. We can say that the equilibrium constant, KEQ, can be expressed in terms of concentration or pressure. And we can deal with pressure if we have gaseous reactions. Now really Kc and Kp are calculated using what are called chemical activities. At low concentration, chemical activity is equal just about to concentration. So we simplify the expression, and instead of using activity, we use concentration. And at low pressure, chemical activity is just about equal to partial pressure. So we simplify the activity expression and express it as a partial pressure expression. But it's important to understand that truly the equilibrium constant is calculated with chemical activities, and chemical activity is contrived to be a unitless amount. So that means that Kc and Kp are also unitless amounts. And also chemical activity is contrived such that the activity of a pure liquid or a pure solid is 1. So that means that we don't need to put, and in fact we don't put, a pure liquid or a pure solid in the KEQ expression. Okay, it's also important to understand that KEQ is calculated with products over reactants. The consequence of that is that if KEQ is much, much greater than 1, this is the much, much greater than sign, that means the equilibrium lies to the right. The products are favored. If we have products over reactants, products in the numerator, reactants in the denominator, right? Products and reactants. The larger the KEQ, the more the products are favored. The larger the numerator is compared to the denominator. Now on the other hand, if KEQ is much, much less than 1, that means the equilibrium lies to the left. The reactants are favored compared to the products. We have a larger denominator value compared to the numerator. And this is a decimal number if it's smaller than 1, right? The smaller the decimal number, the more the reactants are favored. So what if we have a chemical reaction that's not at equilibrium? It hasn't reached that balance point, that equilibrium state or equilibrium mixture. Well, then we can introduce this concept called the reaction quotient, represented with a capital Q. We have that same chemical reaction, and we can say that here we have Q calculated rather with concentration, and here Q calculated with pressure if we have a gaseous reaction. And you'll notice that this looks the same as the equilibrium constant expressions. What's different though is that Q represents conditions, so concentration values or pressure values, that are not necessarily at equilibrium. They could be at any point in the progress of the reaction. They could be at equilibrium or not. If Q is calculated and it's equal to the equilibrium constant, so if Q equals KEQ, then the reaction is at equilibrium. So what if Q does not equal KEQ? What if the reaction's not at equilibrium? Well, let's take a look at that. Let's compare QC versus KC. So the reaction quotient versus the equilibrium constant. And the same comparison would hold true for pressure QP and KP. We have that same reaction. On the left here we have a calculation of QC that's not at equilibrium. In other words, we're using concentrations that are not equilibrium concentrations, and that's calculating for QC. And then let's say over here on the right we have concentrations that are equilibrium concentrations. So that's calculating KC. Remember, KC is using this expression when they are at equilibrium, when we have equilibrium concentrations. So we could say that the reaction progresses to equilibrium, or goes to equilibrium, as this expression becomes equal to this expression. Now, if QC is not equal to KC, the reaction is not at equilibrium, the question is, what do you have to do to QC to get it to be equal to KC? What do you have to do to get the reaction to go to equilibrium? Well, there's two possibilities. If QC is less than KC, in other words, this expression with values not at equilibrium is less than this expression with values at equilibrium. In order to make this bigger, right, if it's smaller and we want to make it bigger to make it equal, we have to increase the products are in the numerator, and decrease the reactants in the denominator. That would make that fraction bigger. Now, another possibility is that QC is greater than KC, so it's bigger. If it's bigger, that means that we need to make the denominator larger and the numerator smaller and drive that value down to get it equal to this value. So we'd have to increase the reactants and decrease the products. If you increase the products, the reaction would shift to the right to get to equilibrium. If we increase the reactants, the reaction would have to shift to the left to get to equilibrium. So here's a quick summary. If you calculate the reaction quotient Q using values that are not at equilibrium for either concentration or pressure, remembering we have products over reactants when we do that calculation, if it's equal to the equilibrium constant, then the reaction's at equilibrium. If the reaction quotient is less than the equilibrium constant, then in order to get to equilibrium, the reaction has to proceed to the right. We have to increase the products and decrease the reactants. That would make the value of the fraction bigger, right? More products, less reactants would make the Q bigger, and it would approach KEQ. It would become KEQ by making products bigger, reactants smaller. If the reaction quotient is larger than KEQ, that means we have to make the reaction quotient smaller. We would do that by decreasing the products in the numerator and increasing the reactants in the denominator. Now we're going to take a look at some sample calculations, but before we do that, let's make a couple points here. First of all equilibrium calculations, including any equilibrium calculations with Rice tables, or you could call those ICE tables, all equilibrium calculations involve either concentration, in which case we'd be dealing with the equilibrium constant with C or Kc, or pressure, in which case the equilibrium constant would be Kp. Now, if you want to convert between molar concentration and pressure, what we do is we use the ideal gas law, and it's pretty straightforward. Take this ideal gas law, P is pressure, V is volume, N is number of moles, R is the ideal gas constant, T is temperature in kelvins. Rearrange it so it looks like this. Just divide V on both sides. Realize that N is number of moles, V is volume, and if volume is in liters, then N over V would be in units of moles per liter. Well, hey, that's molarity, that's molar concentration. So for N over V, we can substitute in capital M for molarity, and we get P is equal to molarity times the ideal gas constant times the temperature in kelvins. Now, another possibility is that you're doing calculations where you're given masses and you want to do equilibrium concentrations with molar concentration, or equilibrium calculations with molar concentration, or you are doing equilibrium calculations and you want to solve for a mass of a chemical. So you want to convert back and forth between mass and molar concentration. In order to do this, the volume must be known. So that has to be given in the problem. So the first thing we do is convert mass in grams to moles, and then we divide by the volume in liters. So check it out. Here we have mass converting to molar concentration. If we take mass in grams divided by molar mass, and we would add up molar mass off the periodic table for any particular chemical formula. If you divide grams by grams per mole, that would give us, well, grams would cross cancel. We'd have the unitless 1 on the top and inverse moles on the bottom, and that's just equal to moles. So moles divided by liters would be moles per liter, or molar concentration. Now, if you want to do the reverse and convert molar concentration into mass, we would just do the reverse of this process. But I would encourage you to not try to memorize the process or put some kind of an equation together with this. Rather, just follow the units. Let the units tell you what you have to do. If you want to get moles, grams divided by grams per mole gives you moles. And then multiplied by liters, or rather divide by liters, moles divided by liters and moles per liter. Go the other way now. If you have moles per liter, you would multiply by the liters, so liters cancels out. Then if you want to turn moles into grams, you would take moles multiplied by grams per mole. Moles would cancel and you get grams. The units tell you what to do there. It is important that you realize that molar mass is involved, though. All right, let's take a look at some sample calculations. Let's say we have one gaseous H2 reacting with one gaseous I2 in an equilibrium forming two gaseous HIs, and that the equilibrium constant in terms of concentration is 50.5 at 448 degrees Celsius. Remember, we always want to know the temperature when we're dealing with equilibrium. We're given these initial conditions, that the number of moles of H2 is 1 times 10 to the negative second moles. For I2, we have 3 times 10 to the negative 2 moles, and for HI, we have 2 times 10 to the negative 2 moles, and that these are all in a 2-liter container. Now remember that the volume of the container is equal to the volume of any gas in the container. The nature of gases is that they spread out to occupy the container, whether they're all alone in the container or whether they're in a mixture. Each gas would have that volume. So in what direction will the reaction proceed to get to equilibrium? The first thing we need to do is calculate molarities, because we use concentration when we deal with equilibrium calculations. So to get molarity for H2, we take the moles divided by the liters. So 1 times 10 to the negative second moles divided by 2 liters, that calculates out to be 0.5 times 10 to the negative second molar concentration, or capital M. The concentration for I2 is equal to 3 times 10 to the negative 2 moles divided by 2 liters. That calculates to be 1.5 times 10 to the negative 2 molar concentration. And for I2, the concentration is 2 times 10 to the negative 2 moles divided by 2 liters, 1 times 10 to the negative 2 molar concentration. We know that QC is equal to the molar concentration of the products raised to their stoichiometric coefficient 2, divided by the molar concentration of the reactants raised to their stoichiometric coefficients 1 and 1, and these are all multiplied. That's important. We're not adding anything. These are all multiplied. So we take the product of whatever we have on the top divided by the product of whatever we have on the bottom, solve for that, and we get 1.3. Now Kc was given to us as 50.5, and we solved that the reaction quotient is 1.3. So the reaction quotient does not equal the equilibrium constant. This is not at equilibrium. And the reaction quotient is smaller than the equilibrium value. So what does that mean? Which way do we have to go to get this equal to this? Well, we have to make it bigger, right? A lot bigger, almost 50 times bigger. Well, that means we need to make the numerator bigger the product's bigger and the reactants in the denominator smaller. So because QC is less than KC, the reaction has to proceed to the product side, to the right, to reach equilibrium. We need a bigger numerator where the products are and a smaller denominator where the reactants are. Here's another example. Let's say we have this reaction where we have one N2 gas reacting with three H2 gases in equilibrium with two NH3 gases. And we know that the equilibrium constant expressed with pressure, or Kp, is 1.45 times 10 to the negative fifth at a temperature of 500 degrees Celsius. We're given the partial pressure at equilibrium of H2 and N2, and we want to calculate the partial pressure of NH3 at equilibrium. Now we know that the equilibrium constant expressed with pressure is equal to this. It's the partial pressure of this product raised to the second power divided by the partial pressure of this reactant raised to the first power. Well, we don't write that one exponent in there. And the partial pressure of this reactant, H2, raised to the third power. So we know what Kp is. We know this pressure and we know this pressure, and we're solving for the pressure of NH3. Now remember, this whole thing has no units, right? These are unitless values when we're dealing with equilibrium constants. So to solve for the pressure of NH3, we do our algebra. We get it, because that's a square value, we got to move these values over here and then do a square root of both sides. It calculates out to be 2.24 times 10 to the negative third atmospheres. Now, since we have atmospheres for our other pressure units, we know that this pressure must be in atmospheres, so we have to make sure that we insert that unit there. Now, what if we did this calculation and it said, hey, what's the molar concentration of NH3? Well, now that we know the pressure, remember that we can convert between pressure and molar concentration. Let's just go through an example of how we do that. So, again, relating molar concentration to pressure, we know this pressure from the previous problem was at an equilibrium where the temperature is 500 degrees Celsius. Now we always need to use Kelvin for temperature, so let's convert that. Add 273 and we get 773 Kelvin. This is all from the previous problem. If we want to figure out the molar concentration, we take PV equals nRT, rearrange it, substitute in molarity for N over V, and we get P is equal to molarity times RT. Now since pressure was in atmospheres, we have to use the R expression, the ideal gas constant, that has atmospheres in it, and that's 0.08206 atmosphere liter over mole Kelvin. That's when pressure's in atmospheres. We need to make sure we use temperature in kelvins, and if we plug in P over RT, atmospheres cross cancels, right? We're trying to figure out what this pressure would be if we expressed it as molar concentration. So we use that pressure, divide it by R, so atmospheres cancels. Notice that kelvins cancels. So we have 1 over liters over moles. So the inverse of liters over moles is moles per liter. That's our unit. And this calculates out to be 3.5 times 10 to the negative fifth moles per liter. So if we had pressure in kilopascals here, we would need to use R in with this expression, so it has kilopascals in it here. If we had pressure in millimeters of mercury, or torr, then we would have to use this expression for R. You can express the ideal gas constant using different pressure values, and then you'll have different numerical values for the ideal gas constant. Okay, here's another sample problem. We have one PCl5 in equilibrium with one PCl3 and one Cl2, and they're all gases. This is our Kp value at a temperature of 500 Kelvin. We know the partial pressure at equilibrium of PCl5 and PCl3, and we want to calculate the partial pressure at equilibrium of Cl2. So we write the equilibrium expression. Since there's one of everything, we have one exponents for everything. Remember, it's reactants divided by, products in the numerator, reactants in the denominator. Plug in our numbers and solve for PCl2. Remember, this has no units when we're using this expression. So we get that PCl2, rearrange that, and we get 1.22 atmospheres. Now, since we're using atmospheres for our other pressures, we would use atmospheres here. Now, it's important to understand that solving for equilibrium amounts, if you want to calculate for an amount of chemical at equilibrium, the math can get a little bit dicey and more involved, and sometimes you actually have to use the quadratic equation. So here's the quadratic equation. If you're solving for x, we know that that's equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a, where we have this as our overall expression. Let's go through an example where we do that. We have 1H2 and 1I2 in equilibrium with 2 HIs. Everything's a gas. The Kc is 50.5 at 448 degrees Celsius. We've used this reaction before. This is what we know that's given in the problem. Our initial moles of H2, INIT is initial, is 1 mole. Initially for I2 we have 2 moles and we have a volume of 1 liter. Now remember that gases occupy the volume of the container, so the volume of each gas is equal to that. So at equilibrium, what's the concentration of H2 and I2 and HI? All right, so first thing we're going to do is calculate the initial concentrations of these chemicals. So the initial concentration of H2 is equal to the moles, 1 mole, divided by the liters, 1 liter. So 1 mole over 1 liter, that's 1 molar concentration. The initial concentration of I2 would be equal to the moles of I2 divided by the overall liters, so 2 moles divided by 1 liter, that's 2 molar, or 2 moles per liter. Let's set up a Rice table. Here's our reaction, that's R, write the reaction out, balanced equation. Now, the initial concentrations for H2 and I2 we just calculated, and we have to make the assumption that since we were given no information about HI, the reaction was just starting out and there was no product yet. So we started with 0 molar concentration of product. The change in the Rice table, right, we have the reaction, the initial concentration, the change in concentration, and the equilibrium. The change is always reflective of the stoichiometric ratio, or the mole ratio, and it's 1 to 1 to 2. So reactants are always diminishing, so we're going to put minus x and minus x. Products are always getting produced, so we're going to put plus on this side, and since we have 2 of those, it's a 1 to 1 to 2 relationship, so x to x to 2x. Again, products are always positive, they're added on as our change, and reactants are always negative, they're going to be taken away as our change. Now if we combine the initial and the change steps, we get the equilibrium state. So 1 minus x here, 2 minus x here, and 0 plus 2x, or just 2x here. So here's our expression of the equilibrium constant using concentration. So concentration of HI squared because of that 2 coefficient, and then concentration of H2 and concentration of I2 each to the first power. We don't bother putting that power of 1 in there. Let's substitute in our equilibrium values. Remember, Kc is always calculated with equilibrium values. So we know that Kc is 50.5. That 50.5 was given in the problem. We know that we have to take the concentration at equilibrium of Hi and square it, so it's 2x squared. Then we have to divide by the concentration of H2, which is 1 minus x, and divide by the concentration of I2, which is 2 minus x. So we have this expression. Continuing on with that solution, we take that expression, 2x squared is equal to 4x squared, right? If we take the quantity of 2x and square it, 2 squared is 4, x squared is x squared. We take this and multiply it out so that we get that expression, right? We use the FOIL method first, outer, inner, last, and then combine our values. Rearrange it so we get that 4x squared is equal to this, and then we take this and multiply it over on that side, distribute that 50.5 by multiplying it by every term inside the parentheses to get the right-hand side of the equation. Set it up so that we have 0 on one side of the equality. So we're just going to take that 4x squared and move it over to that side. 50.5 minus 4x squared is 46.5x squared, and then minus 151.5x plus 101, and that's all equal to 0. And now we have a, b, and c that we can plug into the quadratic equation and solve for x. So we plug in these values and solve for x, and we get that we're always going to get two values for x when we use the quadratic equation. We get this big value and this small value. Now it's always going to turn out that one of these values is impossible. So we know from the Rice table in this reaction the concentration at equilibrium of each one of the chemicals. Here's that Rice table again. We know this is the equilibrium concentration of H2, this is equilibrium concentration of I2, this is the equilibrium concentration of 2HI. It's equal to 2x. So we know these values from the Rice table. If we plug in this number for that value or that value, we're going to get negative concentrations. So using this number for x and solving for the equilibrium concentration of these two chemicals would give us a negative value, a negative concentration, and you can't have a negative concentration. Now it's always going to happen that way, that one of these values would be meaningless. So we can cancel this value out and say x cannot be equal to that. So we use the other value for x. So if we plug this value into this equation, this is the equilibrium concentration of H2. If we plug this value into this equation, this is the equilibrium concentration of I2. And if we plug this value into that expression, this is the equilibrium concentration of HI. Now remember that the units of concentration are all going to be in molarity or moles per liter. Or we can just say 0.065 molar, 1.065 molar, and 1.87 molar. Now you should always check your answer. We know that the Kc expression is this. Let's plug in the concentration at equilibrium for HI here, and remember you have to square that. Plug in the concentration for H2 here and for I2 here, and solve that out, and we get 51. Now that's really close to 50.5, and we would imagine that it's not exactly right on because of some rounding issues. Now that's about as tough as a problem can get. Oops. That's about as tough as a problem can get if you have to use the quadratic equation. I think that was off camera a little bit, so here's how you check your answer. Now, let's take a look at how mass relates to molar concentration, because we said that sometimes happens. So from that previous problem, we just solved for these three equilibrium concentrations. So what if the problem said, what's the mass of HI gas at equilibrium when the reaction occurs in a 2-liter container? Now remember that if we want to solve, if we want to convert back and forth between grams and moles per liter, we need to know the volume. So we have to be specific here that we have a 2-liter container. Remember, the volume of the gas is equal to the volume of the container. Now for HI at equilibrium, we said it's 1.87 molarity. We just solved for that. So that's 1.87 moles per liter. So let's let the units carry us through here. So we take 1.87 moles per liter for HI, multiply by 2 liters so that liters cancels out, and then add up the molar mass of HI from the periodic table. If you add up the molar mass of H and I, it comes out to be 127.91 grams in 1 mole. So we set that up so that moles of HI will cross cancel, and we can get calculated out 1.87 times 2 times 127.91. You don't have to bother dividing by 1. And we end up with 478.38 grams. It's important when you have sequential calculations to not just do this calculation, get an answer, round it, and then do this calculation. It's best when you have a bunch of numbers in sequence to lay them all out in sequence and do the calculations in sequence, and then round only one time at the end. All right, that's it.